world, our planet Earth, revolves endlessly in space. Man, searching for knowledge, directs his studies increasingly toward the space around the Earth, toward the solar system and the universe. He uses sensitive radio instruments to listen to faint signals coming from distant sources in the universe. He uses delicate optical instruments to study the sun. Yet with all this reach into space, one of the most difficult research problems encountered by scientists is the study and measurement of the upper atmosphere surrounding the Earth. The problem begins at a height of 300 kilometers, about 185 miles, in the region called the Ionosphere, and extends to great heights approaching interplanetary space. Here, we see how the ionosphere can reflect radio waves. This characteristic helps long-distance communications, but it hinders the use of radio techniques to study atmospheric constituents above the ionosphere. Rockets and satellites help significantly. Satellites can detect and measure constituents of the outer atmosphere and even the exosphere, as the region beyond is called. Explorer 1 and Pioneer 3 discovered the Van Allen radiation belts. This is an artist's conception of the Van Allen belts. These vast regions above the Earth's ionosphere are composed of trapped electrons and protons. It is true that observations made by satellites have permitted scientists to cross a new threshold into space research. But orbiting satellites and expensive specialized rockets can provide only snapshot observations of the ionosphere. They cannot give us details for a specific geographic location. Continuous observations above the ionosphere for a fixed location are needed. This film is the story of how scientists at the National Bureau of Standards, U.S. Department of Commerce, tackled the problem and developed a new research technique using scatter radar for space research from the ground. It is the story of a search for a location, of building an observatory and an entire research facility. And lastly, it is a heartening story of international cooperation on a person-to-person basis. Let's look at the ionosphere again to understand the problem better. The ionosphere is composed of neutral constituents, ionized constituents, and free electrons. It is the radio properties of the regions of free electrons that permit long-distance radio communication in the so-called shortwave bands. Up to frequencies of about 30 megacycles per second, free electrons reflect radio frequency energy back toward the Earth. But at frequencies above about 30 megacycles per second, the radio waves penetrate the ionosphere. For years, scientists have used the ionoson, such as this model C4, to measure electron density variations. But its use is limited to the denser regions of the atmosphere, such as the F layer at 300 kilometers. Here, there may be up to several thousand electrons per cubic millimeter, or millions per cubic centimeter. But beyond this range, the density of free electrons decreases. Scientists wanted to know how far above the F layer free electrons extended. The problem was to devise a way to measure them. Here we see two atoms of oxygen. An electron detaches from one of them. When detached, it is a free electron and can respond to electric forces imposed upon it. When a radio wave passes by, the electron oscillates with the wave and re-radiates or scatters its energy incoherently in all directions. The problem is to excite these electrons sufficiently so that they will re-radiate enough energy to be detected from the ground. What is needed is an exceptionally powerful transmitter, an extremely large antenna, and a very sensitive receiver. Here are the Boulder, Colorado laboratories of the National Bureau of Standards. One of these, the Central Radio Propagation Laboratory, conducts basic research in the Earth's ionosphere and upper atmosphere and in space. To Dr. Kenneth Bowles, a physicist with the Boulder Laboratories, goes the credit for solving the problem. Here he confers with a colleague. Acting on a suggestion by Dr. W.E. Gordon of Cornell University, Dr. Bowles employed a technique using the incoherent scatter of radio waves by electrons in the ionosphere. This transmits a powerful pulsed radio signal in a narrow beam. The beam penetrates the ionosphere and excites free electrons in the area above. They scatter a weak signal. The extremely sensitive antenna, now acting as a receiver, detects the faint scattered signal which comes back to Earth. The system can detect faint echoes from electron densities as low as 100 per cubic centimeter, such as exist well above the F layer of the ionosphere. Under Dr. Bowles' scientific leadership, the new technique using scatter radar was successfully demonstrated at a field site in 1959. Here, near Havana, Illinois, is a portion of the original antenna used in that pioneer experiment. A breakthrough of great importance had been achieved, promising to make upper atmosphere and space research possible from the ground. The Bureau gave full support to plans to exploit the technique. First, a site was needed where the fullest range of observations and measurements could be made, including studies of the chemical composition of the upper atmosphere. They would be of greatest interest if made near the magnetic equator, where the lines of force of the Earth's magnetic field are nearly horizontal, giving the electron unusual characteristics. The pulsed radar signals could then travel perpendicularly to these lines of force and excite free electrons. This would allow us to observe the gyrations of those excited electrons, determine the characteristic frequency of the ions controlling these movements, and identify the chemical composition of atmospheric gases. Certain of the gases, such as nitrogen and oxygen, dominate in lower regions. At greater heights, regions of oxygen, helium, and hydrogen dominate. With scatter radar, we can learn the heights of these various regions of gases and study the total composition of the atmosphere. Where could an ideal site be found? It should be on the magnetic equator, but as close as possible to the United States to shorten travel and shipping time. These requirements narrowed the choice to South America, and we decided to examine Lima, Peru. Especially important in our consideration was a year-round temperate climate such as found here. Lima, the capital of Peru, is an ancient city, rich in tradition. A city of handsome plazas and broad boulevards, beautiful buildings and art treasures. There would be major construction projects. Could we find skilled technicians and workmen? Engineering students eager to work on the research in the years ahead? Could we depend on local industry, local sources of supply? We were planning a major undertaking and many points had to be considered. We knew that wherever we went, we would need the cooperation of many people and of the national government too. Shipping and port facilities, like these at Callao near Lima, would be important for receiving tons of equipment. We would need import and customs agreements. Good international air service was another key factor influencing our decision. So were numerous other conditions, such as housing facilities. In Miraflores, a suburb of Lima, we found these attractive residential areas. One key to a successful operation in Peru is the Instituto Geofisico del Peru. The Instituto is a scientific research organization of the Peruvian government. We decide on a visit to the Instituto's observatory, one of the world's highest observatories located near the magnetic equator. The trip begins with a spectacular train ride up the Jicamarca Valley through the Andes. This mountain route is an achievement in railroad engineering. It is the highest standard gauge railroad in the world and noted for its numerous tunnels and reverse switchbacks. The train reaches an elevation of almost 16,000 feet at Ticlio. Surrounding peaks soar another 6,000 feet higher. We see llamas at elevations above 12,000 feet. Graceful, gentle animals, they serve as beast of burden and as the Indian source of milk, wool, and meat. Arriving, we pass through the village of Huancayo on our way to the observatory. The area's commercial activity centers around this weekly market. Here, the native Quechuan Indians do all their trading by barter. The Quechuans represent a large percent of Peru's population. Just beyond Huancayo, we reach the observatory. Here, we find scientists from many countries working together. The Scatter Radar project might well result in another mutually beneficial program. This would strengthen the close research ties that have existed for many years between the Instituto and the National Bureau of Standards. From the observatory high in the Andes, we descend again to the seashore to observe the coastline from the air. Peru's coast is arid. The cold Humboldt Current comes up out of the Antarctic and flows past the Peruvian coast, creating the dry climate. It has not rained here for over 16 years. This would be an appropriate climate for our experiment, and these rocky mounds rising from the valley floor would be useful to shield radio signals coming in from low angles. Green growing things, like the vegetables we see being raised here, come only with irrigation. Here in this arid valley, only 17 miles from Lima, is the broad, flat plain we need, with enough space for our enormous antenna. Thus, our search came to an end. We found an ideal location, the Quebrada de Jicamarca. Work was started. Earlier, a treaty had been signed between Peru and the United States, naming the Instituto Geofisico del Peru and the National Bureau of Standards as parties. Now, in August 1960, the site is prepared for construction. A diversion dam is built to protect the site from rare but dangerous huaicos, or mud flows. In the mountains, it rains, sometimes excessively. The runoff surges down the canyon, a flood of thick mud. This massive destructive force loosens large boulders, sweeps them along, cutting deep gullies in the valley floor. In 1961, huaicos occurred, the first in over 29 years. Up canyon, this wire will sound an alarm at the site in case a huaico should come. Work proceeds rapidly on the antenna. Here, Peruvian workers mark the ground and carefully align places for the post holes. Wood posts will be used to support the antenna dipoles. When the antenna is finished, more than 9,000 posts will have been set, covering a 22-acre field. The Peruvian workers proved they could learn quickly. They were soon performing these jobs skillfully. The inserts here being assembled permit the inside of each radiating element to be used as a piece of coaxial transmission line. In this way, the entire antenna is interconnected. Firm working schedules push construction along rapidly. The Peruvians not only contribute good workmanship, but each worker seems to realize the importance of the project. During the peak construction period, over 200 Peruvians were employed here. This provided an important boost to the local economy. With work underway at the site, the first contingent of Bureau staff families comes to Peru. Homes are available for rent in Chaclacayo, beautiful little community with a pleasant year-round climate. Only 10 Bureau employees and their families are in Peru during this main construction period. They are a small but effective group. Each one wants to develop friendships with the Peruvians, to understand their customs and background. Here, for example, Peruvians and Americans together enjoy a Peruvian delicacy, aracuchos, barbecued beef heart. Many problems, potential major obstacles, were ironed out by this grassroots diplomacy. Such mutual understanding and goodwill helps to speed progress on the Jicamarca site. Wives of the Bureau staff do much of their shopping in the local markets. All members of the family speak Spanish. The ability to communicate in the local language is an important factor in the daily lives of these U.S. families in Peru. There is always a wide choice of fresh vegetables, locally produced, and of fruits such as bananas and papaya from tropical eastern Peru. At Jicamarca, the building is ready, a half-acre under one roof. Here is housed the huge transmitter supplied with electric power from nearby Lima. Dozens of skilled Peruvian engineers and technicians work on the project. Some are employees of the Instituto Geofisico del Peru. Others are university students from Lima, getting practical experience in electrical engineering. Peruvian and Bureau scientists and engineers work together, assembling and installing the many systems and components. To continue this international cooperation, other Peruvians with potential technical skills are being trained by Bureau engineers. In regular classes conducted in Spanish, they are taught basic electronics and mathematics. Many of these men, being trained as engineering aides and technicians, will work at the observatory, staffing the 3 8-hour shifts for continuous operation, including operation of the observatory's huge transformers seen here. Weighing up to 27 tons and standing 15 feet tall, these transformers deliver 3,750 kilowatts of electrical power to the transmitter system. Now we go to the large room housing the Condenser Bank. Here, 12-foot tall banks of capacitors stretch for 60 feet. These Peruvian workers are making a final wiring check on the powerful electrical equipment the observatory will need for probing above the ionosphere. These capacitors form a bank having a capacitance of 1,000 microfarads. This bank can be discharged in a powerful electrical pulse rated up to 20,000 joules. In the amplifier room, these electrical pulses are converted into radio frequency power. Each of the 4 amplifiers used in the transmitter was manufactured in the instrument shops of the Bureau. Each amplifier houses a transmitter tube capable of producing over 1 million watts of radio frequency power. The 4 amplifier system is designed to produce 6 million watts of radio frequency power. This maze of pumps, filters, and piping is the water purification and cooling system. It circulates demineralized water through the amplifier assembly. This dissipates the large amount of heat radiated by the transmitter tubes. Heat exchangers cool the water for recirculation. A network of tunnels runs beneath the building. Blowers circulate cool air throughout the passageways. These tunnels contain over 70 miles of cables and plumbing, interconnecting the transmitter components. Cables and coaxial piping enter the equipment rooms through floor vents. Engineers in the control room direct the transmitter energy into the antenna. Here they are seen monitoring every function of the system's operation. Coaxial aluminum piping, made of irrigation pipe, conducts the transmitted and received radio signals through a spark gap and mixer system. This automatically switches the antenna from transmitting mode to receiving mode in millionths of a second. The energy for the radio signal flows through the coaxial piping in these trenches, continuing to the midpoint of the antenna. Each quarter of the antenna is fed separately. Distribution is made to each module. A modular section comprises 1/64th of the antenna. Each module contains 144 antenna dipoles, or 288 dipoles per module. Open wire lines of 1-inch aluminum tubing connect 2 rows of 12 elements each to the central feed point of the module. Power is distributed to the individual radiating elements. This system of feeding permits unique flexibility in use of the antenna and gives it great sensitivity in receiving very weak signals from great heights above the ionosphere. Even with the antenna only partially completed, Dr. Bowles and his staff were able to initiate scientific observations. Here, Dr. Bowles, working in the screen room, is making measurements of electron densities out to 1,200 kilometers. He is using a 160,000 watt transmitter, representing only a small part of the observatory's ultimate 6 million watt capability. Radio stars, previously not known to exist, were already being observed, and other findings of great scientific significance were being made before the system was complete. Here is the trace of electron densities in the 1,200 kilometer range that Dr. Bowles has just recorded. As said earlier, scientists believe that free electrons extend to great heights above the Earth's ionosphere. Early measurements at the Jicamarca Observatory confirmed this belief. Even within the first year of observations, free electrons were detected at well above 5,000 kilometers. Other research will be added. Already, preliminary studies of the planet Venus have been made. Soon it may be possible to detect and measure clouds of solar gas driving toward the Earth, and to study the energy balance between the Earth and upper atmosphere, an important factor in our weather and meteorology. The Instituto Geofisico del Peru and the National Bureau of Standards are partners in what are indeed some of the most exciting radio research experiments of our time, searching for knowledge about the Earth's upper atmosphere, interplanetary space, and the universe, with scatter radar, and important new technique for space research from the ground.